Alright guys, so we talked last time about remembering sine, cosine, and tangent and just like right triangles that exist out in space. But now we want to talk about if I take those right triangles and put them on a coordinate grid. So kind of some things that are a little bit related to that we need to go over first is like sketching angles / triangles on a grid. Like, how do we do that? Okay. So an angle is considered in standard position so when I'm drawing an angle, I have like two rays coming off of it, boop, boop. And you are in standard position if the initial side of your ray, so kind of where you start, so initial ray is on the positive x-axis. So in this little example here, your initial ray always has to start here. And then I kind of come out from that and get another ray. So I have my initial ray coming out always on positive x. And then depending on my angle, I come up from that and get another ray, and I end wherever I'm supposed to end. And so that's called your terminal ray, or your terminal side. So terminal ray is kind of done however big your angle is. So ends after you travel x degrees. So however many degrees you're supposed to go. So for instance here, when it says sketch 250 degrees, I can do this because in a coordinate grid, we know that each quadrant is 90 degrees. So if I think about taking that terminal side here and like shifting it up, here's 90, now I've gone 180, and then another 90 puts me at 270, so it's kind of too far, and it's a little bit of an approximation, but your terminal side ends up here. And now it's important to show which way you traveled, and if you notice, I went counterclockwise, and you should always go counterclockwise. That's why we name our quadrants as such, like this is 1, 2, 3, like we name them counterclockwise, so we always travel counterclockwise in math. And so I need to kind of show that that's how I traveled with this here, that we got 250 degrees. So I sketched that right there. This one we're not going to talk about yet because we don't know what that is yet. We'll come back to that next time. So the thing is, we can also have coterminal angles, and what it means to be a coterminal angle is an angle that terminates at the same spot as another one. So they end at the same spot. And so that's why it's important to put this little arc here showing that I traveled this way, because if I go in the other direction, if I go if I go clockwise, I can end right there as well, but I didn't travel 250 degrees. If you go all the way around the circle, so 360, and take off the 250 that I did travel, I actually traveled 110 degrees in this direction. Now if I go in this backwards direction, then you have to put a negative in front of it. So a negative implies that you went clockwise. So negative 210 would be coterminal with 250 because they end at the same spot. So we can talk a little bit more about how we would sketch some angles, like maybe I'll do a few more examples and come back to that, but what we really need to talk about are reference angles, because that's how we get our triangle. So I can't really get a triangle out of that huge angle there, but if we think about how that was drawn, like this angle right here kind of came out like this, a reference angle is an acute angle at the center, so at the origin, related back to your x-axis, so related to the x-axis. And so if I were to take that 250 angle that I sketched out before, I wouldn't actually be using 250 anymore. I would be using an acute angle that is centered at the origin, right here. So there would be theta, if you remember theta. Related back to your x-axis. So I'm kind of dropping down a line right here to get just this angle right in there. So it's to your x-axis, not to your y-axis. And that's kind of how we get our right triangles. So that leads me to our little poof book right here, okay? So but before I actually fill all this out, I'm gonna draw a picture over here because I don't have enough room there. If we are talking about our x and y axis, like this, if we are sketching out angles, and I end up with my terminal side being in that first quadrant, I can get my reference angle, again, by dropping down that perpendicular to get to the x-axis, and theta is here. Now if you think about it, when theta is here, and if we're thinking about sine, cosine, and tangent, and the Pythagorean theorem really, if theta's here, this is the opposite side. Now, this is how high you went, and when I'm talking about how high I go, that's the y value. Adjacent right here is how far I went, like how long I went or how much I ran, so that's like my x value. And then this right here is my hypotenuse, which in terms of triangles on an xy plane, we call that the radius. This is kind of like the radius of a circle going round and round and round. So you get that right there, which is so cute. Now, if my terminal side ends in quadrant 2, again, we can drop down our perpendicular so that we get our right triangle. Theta is always at the center related to the x-axis. And again, this is my x distance that I traveled. Here's y, and here's my radius. And these are important because I want to talk about our trig functions in just a second. Or maybe my terminal side ends in quadrant 3. And so if I bring that perpendicular to my x-axis, because theta is always related back to x, we have our x length right here, our y height right there, our radius. Or, you know, like we could have our terminal side end in quadrant 4. And they can end wherever, like it's kind of an approximation depending on your angle. I drop up that perpendicular because theta has to go to x. And this is my x distance that I traveled, y distance, r distance. Now that's important for a couple of things, because I might be able to plot a point and know that xy distance and find r by doing the Pythagorean theorem. So like r squared is going to be equal to x squared plus y squared. And so I can solve for r, the radius, by taking the square root of x squared and y squared, when those are like ordered pairs that I could graph, which is super cute and fun. So in this triangle here we got theta, we got y because that's up and down, x, and then r. Now the other interesting thing, the thing that I love, and this is kind of important, is if I think about sine, cosine, and tangent. So sine here of theta is going to be opposite over hypotenuse. Cosine is going to be adjacent over hypotenuse, so x over r. And tangent is going to be opposite over adjacent, so y over x. And if you think about it, if I'm in this quadrant, all these numbers are positive. So they are all positive here. If I go to this next quadrant, sine of theta is going to be opposite over hypotenuse, so y over r. Cosine is going to be adjacent over hypotenuse, so x over r. And tangent is going to be opposite over adjacent, so opposite of that is y over x. So they're the same no matter what quadrant you're in, it seems like. I mean, we'll do one more to check. But if you think about it, in this quadrant, because you're in quadrant 2, y is always positive, but x is always negative. So y over r will have to be positive. X over r, though, has to be negative. And tangent has to be negative because x is negative. And so if you're in this quadrant, only sine is positive. So sine is positive, you're all positive. Okay, so if we're in this quadrant down here, quadrant 3, sine of theta is opposite over hypotenuse, so y over r again. Feels safe to assume that. So cosine is adjacent over hypotenuse, so x over r, and tangent is opposite over, so y over x. So it feels safe to assume that's what sine is always going to be. So sine is always going to be y over r, cosine is always going to be x over r, and tangent is always going to be y over x, which is super fun because that's slope. Oh my god, I love it. Anyways, if I'm in this quadrant, x is negative and y is negative, so sine's going to be negative because y is negative, cosine's going to be negative because x is negative, and tangent is going to be positive because a negative divided by a negative is positive. So in this quadrant, only tangent is positive. Alright, last but not least, in this quadrant, we know, hopefully now, that sine is going to be y over r, cosine is going to be x over r, and tangent is going to be y over x. We just got to think about the positive and negative stuff now. So in this quadrant, x is positive, but y is negative, so sine will be negative, cosine will be positive, but tangent will be, so the only one in this one is cosine, which is kind of what I guessed because it was the only one we hadn't talked about yet. So you kind of have this thing where some people will make little ways of remembering this, because this is always going to happen. I know this crazy picture, but like ACT sucks, or CAST, or all students take calculus, which is the one I like the best because it goes in that quadrant order. So all students take calculus, because why not? Okay, anyways, after that mess of a thing, let's actually look over here. So we have our sine, cosine, and tangent that we figured out because they always ended up the same. We can also do those reciprocal functions that I talked about last time. So cosecant is sine's reciprocal, so just swap those, so r over y. Secant is cosine's reciprocal, so r over x. And cotangent is tangent's reciprocal, so x over y. So that's fun. But we can use all of that to actually do really clever things. So here's kind of where it all comes together. So let the square root of 21, comma negative 2 be a point on the terminal side of an angle theta in standard position. So that's why I need to know how to sketch an angle, right? So standard position means that the initial side of my angle comes out on positive x, and I need to travel counterclockwise, theta degrees, although this is actually telling me a different way to do it. So they're telling me to plot this point. So the square root of 21 is positively somewhere over here, and then negatively down 2. So that point exists in quadrant 4. And so if I draw the terminal side going through that point, now we want to talk about that reference angle. So the reference angle is always referenced to x, and then I can draw in that perpendicular right there to get my right triangle. Okay? And because this point was at square root of 21, comma negative 2, I traveled over 21, no, square root of 21, and then I traveled down negative 2. So those are my x and y values. So x is root 21, y is negative 2, and I can find r by doing the Pythagorean theorem because I have two sides of a right triangle. So if I square this guy, it's 21. If I square that guy, it's 4, and then we add them up for 25, and then we square rooter to get r. So the radius is 5, which is great because now I know all of the triangle, and I can find all the trig ratios. So sine of theta is opposite over hypotenuse, but it's also y over r, so negative 2 over 5. Cosine is x over r, so root 21 over 5. And tangent is y over x, so negative 2 over root 21. Oh, poo, and we gotta rationalize that, which is just gonna put the root 21 on top and 21 on bottom, and I can't divide there, so final answer for a tangent. My cosecant, secant, cotangent are just reciprocal functions, so we just flip them. So 5 over negative 2, oof, 5 over root 21, which I'm going to have to rationalize that. So 5 root 21 over 21. And then cotangent, I actually go back to the start and flip there because then I won't have to rationalize, which is super nice. Okay, so that's kind of how we can do that. Another fun, interesting thing that we can do when I have an angle and then triangle drawn in the xy coordinate plane is I can find another function when I know one of them. So they're telling me that the terminal side of theta lies in quadrant 2. So we're in quadrant 2 like this, which means that when I drop down my perpendicular, theta is here. And they're telling me that cosine of theta is negative 5 over 13. And I know how I found cosine of theta. That was x over r. And x in quadrant 2 is always negative. So the negative 5 is my x value, is how much I traveled in the x direction. And then 13 is my radius. So 13 goes here. Which if I know two sides, I can find the third by doing the Pythagorean theorem. So we can do 13 squared equals negative 5 squared plus I don't know squared. I should call it y because it is y. So we got 169 equals 25. And then we want to subtract, so 144, and then we want a square rooter for 12. So this height here is 12, which is super important to know because if I want to find sine of theta, sine is y over r, so 12 over 13. And it's positive because sine is always positive in that quadrant. Okay, so example 3 is similar. Find a trig ratio when you're given a trig ratio, so just like that last one. So we know that sine of theta is negative 3/5, and maybe it feels weird because like the negative isn't assigned to a value here, although it should always be assigned to x or y. And then we're in quadrant 4. So if we think about sketching theta, quadrant 4 is here, so my terminal side is here, which means theta is there. And we're trying to find tangent of theta. So if I know sine of theta is y over r. So the y value here is 3, and it definitely needs to be negative 3 because I went down 3. So r, my radius is 5, and then I can do the Pythagorean theorem to get this length right here, but if you remember, 3 and 5 are part of the Pythagorean triple, and so your other length there is just 4. But I mean, you can do x squared plus y squared equals r squared. And so that's super helpful because then I can find tangent of theta. Tangent of theta is going to be y over x, so y is negative 3 over x, which is 4. And if I'm in that quadrant, tangent should be negative because the only thing that's positive is cosine. So guys, these are kind of harder examples, and I think what I'm going to give to you to try, I think I'm mostly going to have you sketching some angles, and maybe there'll be a little of this. Yeah, why not? That's fun. Okay, good luck.